Alrighty guys, welcome back to another round of homework help with Mrs. Grady. We are taking a look at web assignment number 7 for our unbalanced forces unit. And what I'd like to begin with is this question. There's only 2 on here, but this one might throw you right away because it doesn't seem like the problems that we've solved before, right? We've got this mass going down an inclined plane. All right, it's 2 point. All right, let's try that again. Not happy about that. Let's try this one more time. 2.3 kilograms. All right, it's going to slide from rest, so our initial velocity is going to be 0, and it's going to go down the inclined plane. The time it takes to do that, you notice I'm not drawing a free body diagram right now. I'm filling in parts from the question, and it seems a little bit different than the problems we've done before, and you would be correct about that. All right, so the reason it's different is not because we haven't dealt with inclined planes, it's because we're being given different information. In fact, this information, distance, time, and then of course our mass, this is really like there's nothing about friction, there's nothing about normal force, what the heck is going on? The big question here is what is the net force? And you say, okay, I know 2 equations for that. I know what Newton said, and I know what Grady said about bigger minus smaller, but I don't see any other force mentioned here. I could, I don't know if there's any friction at all. I could start drawing stuff, but the truth is they're giving you information about the motion. They're giving you information about a VT graph is what they're doing. That's because the idea here is to go in a different direction. It's not that you cannot use forces, it's just that hopefully you remember that the slope of the line is the area. In this particular question, all right, my delta x, which is my area under the curve, that's going to be 0.73 meters. I'm looking to find this acceleration because I can take that and put it right there. And then I will be able to find the net force. So if you're asking yourself, what do I do now? Well, we know our time. It's 0.43 seconds. It'd be really handy if we knew the VF. So I would suggest using your area under the curve for that. It's a nice little triangle, so we can use our area of a triangle formula. Figure out VF, then use that and use the slope formula and figure out the acceleration. That would be my suggestion. Just a reminder, the reason I gave you this question is to remind you that acceleration is the link between motion and forces. It's the one key thing we have in common. So whether you begin from the forces standpoint, which is kind of what we've gotten used to, or you start from the motion standpoint, it's the same acceleration, and you can go back then either from forces to motion or from motion to forces. That works just as well. All right, let's take a look at this next one. Hockey puck hit on a frozen lake. Starts moving. All right, so you have an initial speed. All right, so we're given an initial speed. And you're given time. And oh, look, here's a final speed. Again, this is looking like motion. Okay, I don't know. Oh, Java update. Hopefully that's not showing up in our video too much. Let's get that. Oh, luckily it disappeared. It just made a funny little noise. I don't know if you heard that or not. It just makes a funny noise. All right, so we're given time, we're given final speed, average acceleration. Again, we're going back to that VT graph. All right, we are looking at this. Now notice I didn't go all the way down to the 0 because it doesn't say that it stops. It's got a final velocity here, it's got an initial velocity here. If you're looking for the average acceleration, well, we're given the time. We're still looking just for the slope of that line. If I want to know how far it goes, well, then that's going to be a whole area under the curve thing where we have a triangle and a rectangle. But it does not appear that we're going to need that. So that being said, let's see if I can get this one labeled a little bit. We start out with a speed of 14.3 meters per second. We end up with a speed of, in this case, 6.4 meters per second. You know the time. The time is, in this case, 6.7. So whatever your values are, you at least have them. Use the slope formula to figure them out. Just remember that you do not have a VI of 0 here. You only have TI of 0. So once you find your acceleration, that's good. What is the coefficient of friction between the puck and the ice? Now we're going to make the jump from motion to forces. So with that being said, let me change colors here and we'll move to a free body diagram. So if that's the puck on the ice, What do our forces look like? Well, these are the easy ones, right? Let's assume that we're moving this way. All right, we're going to have the force of friction going to the right. There is no applied force. There's no fourth arrow here. All right, remember, you don't need a force if something like, let me rephrase. The force that's being applied here is actually slowing it down. That whole like hitting the hockey puck thing, that happened prior to the motion. And that since the hockey stick is no longer in contact with the hockey puck, there's no fourth arrow here. So this is my free body diagram. As you can see, I have an acceleration going this way because I have a net force here. It's another reminder that if I have a net, if these are opposites, you're slowing down, which is exactly what's happening here. All right, so we want to know the coefficient of friction. Well, you know the coefficient of friction formula is going to be friction over normal, right? Normal is going to be easy because I just have to do mg for that. Those are equal and opposite. The force of friction is going to be a little bit tricky, but actually not so much. It's the only force going in the horizontal plane, right? So this friction force, this isn't part of the diagram, I'm just doing this for space, okay? The friction force is actually the net force. We say bigger minus smaller. Well, there's no smaller. It's just bigger. It's just friction. So mass times acceleration equals the force of friction. It's the only thing causing that acceleration. And oh, look, lo and behold, you should know the acceleration from part A, and you know the mass already somewhere, don't we? No. Well, isn't that something? Ooh, it adds another layer on here. But no worries. We got this, you guys. We got this. Let's look at it from just a variable point of view. Notice what I did here. I said Fn is going to be equal to mg, but look what I just did here. Ff is going to be equal to ma. Let me give myself a little bit of space here so we can see what's going to happen. Oh, I love when we do this. This is a little more advanced. All right, so let's rewrite this so that we can see everything. All right, so here's my arrow. We said normal force is mg. We said friction force is ma. Look what happens. Bye-bye. Away it goes. We can take our acceleration and divide it by little g of 9.81. And boom, you've got the coefficient of friction. Ta-da! Magic. Variable math magic right there. All right, well, hopefully that helps you with your homework. If you have any additional questions that you need personal attention with, you know where I'll be tomorrow morning. I'll see you then.